great pleasure to welcome Professor Fan Li from Duke University as our seminar speaker today. Fan is professor at the Department of Statistical Science and also the Department of Biostatistics and Bioinformatics at Duke University. Her main research area is causal inference with expertise in propensity score methods, clinical trials, natural and cozy experiments, and also Bayesian causal inference. Today, she will be presenting her research on covariate adjustment in randomized experiments with incomplete covariate and outcome data. Over to you, Fan.
Thanks, Lee, for the nice introduction, and nice to meet everyone. And so let me share my screen. Okay, so you can all see it, right?
Yeah.
So today I'm gonna talk about some work. So this work, so today's talk is almost like a half tutorial or half overview of the topic and half of some very recent work that I've been working on. And so again, the general topic is the covariate adjustment in randomized trials with missing data. So just give you some overview. The randomized trial, sorry, it's just my Zoom is a little bit busy, so I need to. Okay, so randomized control trials, we all know, are gold standard for evaluating efficacy and safety of new treatments. And why is that? Because randomization ensure balancing both, in theory, ensure balancing both measured and unmeasured covariates in large samples, right? But that is again in long run and in large samples. But we know that in finite sample, and actually particularly in small study and a single trial, very often you have chance imbalance in baseline characteristic. And so this is, most of the time, this is not a big concern. But when you have a small studies, and also if the chance imbalance happen actually in some important predictive outcome of predictive covariates, particularly like this baseline outcome, then so their theory and also practice show that if we can adjust for such imbalanced covariates, we can increase precision in the treatment effects estimation. Again, this is very helpful in small data, in small samples, because again, you want, if your effect size is not big to begin with, and then you have, a little bit increase in the efficiency helps. So that is kind of the background. And so then just some general setup. Okay, so in order to talk about, but today what I'm going to talk about is actually covariate adjustment, how to do covariate adjustment when you have missing data. But in order to get that, we first need to talk about covariate adjustment. So it's kind of a long detour. So imagine we have a RCT with n units and with two arms. So I use Z to denote the binary treatment indicator, and then assuming pseudo stable unit treatment value assumption. Again, that's a common terminology in causal inference. So each unit has two potential outcomes, y1 and y0. And of course, we only observe one of the two for each unit. And then you have a bunch of baseline pre-randomization covariates, xi. So the key thing is, what is the estimate? So in this talk, let's say we focus on this thing called average causal effect or average treatment effect. Essentially, it's the expectation of y1 minus y0 average over all the units. And of course, because we are in randomized experiment, so the treatment group and control group are the same. So actually, ATE is also the same as average treatment effect for the treated. But of course, that's not the case in observational study. But again, our setup here is in a randomized experiment. So what are you going to do to estimate this treatment effect? Of course, in randomized experiments, the treatment is randomly assigned with a fixed probability for every person. So in other words, the probability of Z equal 1 is just R. This R often is set to be 0.5, then as a balanced design, sometimes some other number, but the thing is it's fixed for everyone. And so we also know on the randomization, there's basically no confounding. So it's very easy. The ATE is just estimated by the difference in means between the treating group and the control group. And so that's the so-called intention to, sometimes known as intention to treat or unadjusted estimate difference in mean estimated, which is just wrote here, right? Just calculate the difference in mean in the outcome, and then you're done, because this is unbiased and all is good. And why is that? It's because of randomization. So this is all simple. Okay, so as I mentioned earlier, you have the thing is, well, when you have chance imbalance in the covariates, then what should you do? Well, then people say that then there's actually originates from Fisher. People, no, let me see, where is he? Oh, sorry, I skipped the slides. No wonder why I was thinking why I'm so okay. Well, good. I'm going to say it. So again, the story is when you have chance imbalance in important covariates, if you adjust it, then you can gain precision. Okay. So how do you do that? So normally there are actually two different approaches, but they are asymptotically equivalent. The first one is called outcome regression, or OLS, or ANCOVA. And the second is propensity score weighting. Again, both of the methods we're going to introduce momentarily. But they're asymptotic equivalent. So this is all sounds good, and both methods are relatively simple. But when I first got into this problem, I realized one thing is people in practice don't use it that often. I work a lot with medical researchers. I actually don't see too often people in medical papers, people report covariate adjusted result. Okay, so then I talked to my collaborator, and so they're saying that, well, look, all the data we have, almost all the trials data we have, no matter how careful we are, they're always missing data. They're missing data in covariates and outcome, and actually both in covariates and outcome. And remember, we're talking about covariate adjustment, right? So you either do OLS or you do propensity score weighting. But the point is that if you are having missing data in covariates, you first have to deal with the missing data in order for you to actually proceed with covariate adjustment, right? Remember, to most people, to most doctors, medical researchers, covariate adjustment is already kind of a bonus analysis, a secondary analysis. And so simplicity is a key. So if you already have missing data, and then you tell people, oh, you can go to do imputation, you multiple imputation, all that kind of thing, then this kind of additional complexity, people just don't want to do it. So that's really, it's very, very practical. So in theory, this covariate adjustment can help. But in practice, because this very prevalent missing data issue, even tiny bit of missing data makes the method much more complex to use. And so there's not much guidelines, so people don't use that, right? So again, people ask the question, worth it going the extra mile in covariate adjustment to deal with missing data? And actually how to proceed? Is it really worthwhile? So that is kind of lead to the research topic I'm going to talk today. So again, as I already mentioned the setup, so I also talk about the unadjusted. Again, this is most people reported. They just calculate the difference in mean, and then that's unbiased, and then they're happy, right? But as I earlier mentioned, that when you have covariate chance imbalance, you can do covariate adjustment, and I mentioned there are two different ways. So here it is. So again, assuming X is centered, so the data. So the first one is very simple. Just say, okay, you just fit this simple linear regression. It's y given z and x, and the interaction term between z and x. And again, x is a bunch of, can be a vector of covariates, right? So in this case, the coefficient, the ordinary square estimate of the z coefficient is a consistent estimator for tau, for the treatment effect. And Ling in the landmark 2013 paper just showed that it is asymptotically more efficient than this difference in mean estimator. Again, Ling's result is very strong, because his result actually showed that it doesn't matter how you adjust for it. Okay, so like he said the result is that this consistency actually holds for regardless of whether the true model is the it's linear. And again, he also pointed out one important thing is it is crucial to include the full set of X and Z interactions. So putting the interactions is very important. Actually, the weaker version of this result, well, low coefficient result, was obtained earlier by Theadis and co-authors in 2000s. But the linked result is it's kind of seal the deal. And then there's some limitation of this approach. Again, this is just pure, this outcome model have nothing to do with whether the truth or not. The result is this OS estimate of Z coefficient is consistent regardless of whether the true model it is indeed this model. Okay, so so that's why it's very very strong. So of course the downside of this, some downside of in practice is that, well, even though the consistency is also there, but if your outcome model is misspecified, is far away, for example, from this model, OS model, then actually it can decrease precision. Okay, so the consistency is also there, but the precision still depends on, you know, this is correctly specified. And also in practice, really, if you have a lot of baseline characteristic, so the theory basically say that you have to include the full set of interactions between Z and X treatment and the covariates. Then imagine if you have small sample, you have a large number of baseline characteristic, you include all of this, then it's really just the variance actually can be high. And another problem is that, well, imagine if you have binary outcomes or categorical outcomes. Well, yes, you can still fit a linear model, right? But that's kind of weird. You're fitting a linear model to a binary or categorical variable outcome. And that's even more of an issue. Problem is especially if you have a real binary outcomes, this is actually can be unstable. Sometimes you cannot just get results. So some of the finite sample kind of practice guidance is usually, okay, so it's usually important we don't adjust for all the covariates, but usually it's very helpful to adjust for first imbalanced and second predictive covariates. So this is like, if some covariates that they are balanced, then there's no point to adjust for them. And if they're actually not predictive outcome, then there's no point, right? But so it's important to focus on the imbalanced predictive covariates for efficiency gain, particularly like baseline outcomes. If they are imbalanced, then it's good to adjust for them. So this is the first approach. The second approach is so-called propensity score weighting. So this is, so we know, so what is propensity score? Everyone knows propensity is just a probability of Z equal 1 given X. Okay, so, well, let me say here. So of course, in randomized experiment, we know the true propensity score is just R, which basically is randomization probability, the fixed probability, right? So what we are talking here, essentially, in the covariance adjustment in RCT setting, the propensity score is just a one-dimensional summary. It's kind of a working score. It's a summary of the baseline covariates. It's not really the treatment assignment probability. Okay, that's just again purely a summary. So then another thing is, once we have propensity score, we can define something called balancing weights. What is the balancing weights? Balancing weights basically look like this. It's basically for the treatment group, it is H is a pre-specified function, and I'm going to talk about it in a moment. So H divided by EX, and and for the control group is HX divided by 1 minus EX. Okay, so this is any weights for any H, the pre-specified function of the covariates, this kind of weights called balancing weights. And so give you two prominent examples. The first one is everyone knows is the IPW. One HX is just equal 1. Again, this is pre-specified. This is just our old friend IPW, right? And if the HX is EX times 1 minus EX, is this thing called overlap weights. Again, it's something I have developed over the last 5 years. Basically, each unit is weighted by the propensity of being assigned to the opposite group. So both of them just examples of balancing weights. And so So general form of propensity score weighting estimate, PS weight estimator, is just a weighted average of the treatment group, of the outcome in the treatment group and the control group. Okay, so you can use IPW and use overlap weights. Again, in observational study, whether you use IPW, overlap weights, or some other weights, the target population is different. The estimate is different. But in the context of covariate adjustment, all of this, it doesn't matter. This is, as I said, the propensity score is a working propensity score because the true propensity is R. So it doesn't actually change estimate, but both of the IPW and overlap weights is just a different way. It's a way to actually do covariate adjustment, so that to achieve efficiency gain. So that is the idea. Anyway, the point is that you can also use propensity score weighting and use different, as long as you're using balancing weights, this kind of weighted average difference in the weighted average between two arms will be your covariate adjusted estimate of the treatment effect. And so, of course, as I mentioned, that the E is just a one-dimensional summary of the baseline characteristic, and usually we estimate it from a so-called a working model. For example, use a logistic model, right? So and again, we have shown, and Williamson et al. Has shown, like, so ordinary square and the PS weight. So the previous, this approach, the ordinary square and the propensity score weighting, they are symptomatically equivalent. Okay, so, and also in many cases they have very similar finite sample, similar performance. But weighting obviously weighting actually has a few finite sample advantages. So first, it doesn't, if you look at this approach, it doesn't really build a model. It doesn't specify any model for Y, right? Unlike OS, you specify a model. Okay, so that is, then that avoids the outcome model misspecification, and in some sense, it also avoids people going on a fishing expedition, try to fish for the best outcome model. So that's the conceptual thing. And second is, it's also, this is the same regardless of outcome types, whether it's binary or continuous or rare outcomes, it doesn't matter. It's all this weighted average. Okay, and another interesting thing is actually particularly overlap weights, as I'm going to talk in a moment. Overlap weights has this very interesting phenomenon property called exact mean balance. So it basically leads to exact mean balance of the covariates. And so we find actually in the finite sample, this definitely improves the efficiency and also give you the phase validity because it's kind of balanced the mean, reach the exact mean balance. Again, I will talk about it in a moment. So this is all good. This is all like, so, and up until now, this is all pretty well known. Okay, but as I mentioned, the main problem really in practice is you have missing data in both covariates and outcomes, right? So then what should you do? Okay, so in the literature, the study of these topics usually separated in talking about missingness in covariates and missing in outcome, because we know that these two things actually are of very different nature. So let's just think of when you have covariate, when you have missing data only in X, only in covariates, what do people do? Well, the first thing is you don't do anything. You just use the difference in mean unadjusted analysis. Or another approach called complete unit, basically use only the fully observed units in the adjustment. Okay, if any unit have any missing data in covariates, then you just throw them away. This doesn't sound like a good idea immediately, And then another approach is called completed covariate. Basically, when you do any adjustment, you only use covariates that is fully observed. Again, this also doesn't seem to, it's very restricted. And another approach is called missing indicator. It's basically include the missing indicators for each partially observed covariate as additional covariate in the study. And we're going to talk about this approach a little bit later, and this turned out to be very important. Another approach is imputation, either single imputation or multiple imputation. It's just, okay, let's first impute the missing X and then use your favorite software, or you use whatever method, I usually people use like mice or whatever, that kind of approach. First impute the missing X and then conduct adjustment on the complete data. Again, if you have any question, let me know, okay? Can stop me at any time. But so far, this is all just a kind of introduction of the background. So you can see there are plenty of methods here, right? So again, so there are many methods like the imputation, for example, imputation. Is it really worthwhile to conduct, say, multiple imputation over single imputation? Or actually, does the quality of the imputation matter a lot, right? So there are actually plenty of work in this space of missing covariates. So from their empirical and then some simulation studies, the consensus kind to be this, is that we all know complete unit analysis is biased, and complete covariate is unbiased, but it's very restricted because if you only have like 1% of missing data, one covariate, even that covariate is important predictive covariate, then you're going to still throw it away. That doesn't seem to make any sense, right? And also earlier, the people noticed that it's important to include missingness indicators. And also plenty of simulation has shown that they find actually there's a very little difference between specific imputation methods. And for example, multiple imputation actually doesn't help comparing to the much simple single imputation. And just in general, it seems that there's a little difference between the different imputation methods. And another question is, how does actually the missing data mechanism of X affect all of this result? So those findings, again, they're all from empirical and simulation studies. So the theoretical justification has been pretty elusive because theory, this is actually not too easy, and just think of how to frame the problem is hard. And another thing that I noticed that there's a very little work in the missing data in the case of when you have missing data both in X and Y. Okay, this is mostly for X. So until last year, actually the paper is just this I would call it really a very important theoretical advancements by Zhao and Ding in the JASA paper. Again, it's IMPRESS, this paper. So they did a basic theoretically kind of solve the problem. So what they did is they actually proposed, they did a lot of theory, I'm gonna summarize here. So what they did is they proposed a modified missing indicator method. So, okay, so first, what is a missing indicator? So to make life easy, I just consider a case that I only have one partially observed covariate, say X, okay? So the Rx is just a missing indicator for each unit. If one is observed, if 0 is missing. Okay, so what is their approach? They're just saying that you can do this model, again, according to Ling's approach, right? You need to have interaction, okay? So what they do have is they have interaction, but what is important, it is that you include, again, I only consider the case have only one covariate X, does it just make life easy, partially observed. So you put the missing indicator here, and you also put this interaction between the covariate and the missing indicator. And this is then the interaction term of between the treatment and this two things. So in other words, if we look at this guy, if you look at, oopsie. So in other words, if you look at here, this two essentially is like you can view this as almost like an augmented covariate with missing data. So you have missing data indicator. You also have this interaction term between X and Rx. What is really effectively do, it can easily show it to yourself. It's effectively impute all missing X by 0. Okay, if anything is missing, then it's 0. So you actually don't need to do any imputation. So this approach. Okay, so this is what they call the modified missing indicator model. So what they show is very important. So what they show, they were able to show that the ordinary square estimate of the coefficient, again, everything centered here, okay, of the coefficient of Z here, which is the treatment, is asymptotically more efficient than unadjusted, the difference in mean estimated. And remarkably, they show this is regardless of the missing data mechanism of X. So really, it doesn't matter what's the missing data mechanism here, as long as the missing data mechanism is independent of the treatment assignment mechanism. They show that this based on this model, the covariates is actually the OS estimate is more efficient than unadjusted. So the point is that and then they also show that theoretically this is basically defines a minimum specification that ensures efficiency gain. Of course, you can put more and more stuff to this model, but this is the minimum specification that ensuring the efficiency gain. This result is really pretty remarkable, right? And then also they show, basically theoretically, they show that doing this, actually the choice of imputation, once you do this model, the choice of imputation method and the validity, even the validity of the imputation model matters very little. Well, that's not surprising, because if you look at the form, this interaction term essentially effectively impute all missing data by zeros. So it doesn't, so obviously you can just impute by zeros essentially, right? So in practice, so this lead to a procedure in practice is you can center all the covariates by its observed by its observed mean, and then impute all missing covariates just by zero, impute by zero, and then create all these missing indicators, and then essentially fit this model, this missing indicator model, right? And then take the ordinary square estimate of the coefficient of z. Then that's it. That's your covariate adjust estimator that for the treatment effect that adjust for the missingness in X. And this has all this theoretically guaranteed the efficiency gain. So this is really a very remarkable result. And this is, this is basically justify an old approach, this missing indicator, but this clarified what the importance is actually all these interaction terms, right? And of course, then the question become, well, I saw the authors, both of the authors, I know them pretty well. I asked them, well, actually, great, congratulations, great result. But how often do you have missing data only in covariates? What if you have outcome also in outcome? How do I proceed? And does this theoretical nice property still extend to there? And under what conditions? And also another thing, because I did the weighting stuff, right? So I'm curious. I just say that, well, this all looks great, but how about weighting? Can I also doing weighting? And in that case, how do I specify the working propensity score model with missing X or Y and or Y? And also, does the asymptotic equivalence between the ordinary square and the propensity score weighting still hold when I have missing data? So I have all of these questions, and then we start to do some work together. So to answer the first question, one of the first questions. So what we did is we actually the PS weighting. So we start to work on PS weighting with missingness only in X. Again, I want to focus on PS weighting. So again, for simplicity, let's just omit all the fully observed covariates. I denote as V, and let's just consider a single partially observed covariate X. Okay, so in this case, it's actually not too hard to specify. So we can also do propensity score weighting. We can just again assume we can specify a working propensity score model with missing value in X, just like this. Essentially, the propensity score is also missing indicator. You put the missing indicator there, and then the interaction term between X and R. As I mentioned earlier, this effective impute all the missing X by 0. And then that you can just calculate your working propensity score, and then does the same thing as the, in this particular case, I actually would recommend to use overlapping estimator. You can use IPW, but I decided to use overlap weight for the reason I'm going to talk in the next slides. So you can, once you have this estimated propensity score with missing data, missing X, then you can just plug in, calculate the weighting estimator. So why I want to use overlap weights is because you can actually pretty easily show that the working propensity score estimated from this model, from this working propensity score model, it is if you use MLE, the result overlap weights can lead to exact mean balance of any indicator that in the both of the missing indicators and also the basically partially zero imputed covariates. Okay, so in this, like again, this is just the form. Is that the point is that use this kind of use overlap weights, you get the exact mean balance. Again, why do we care about exact mean balance? In this case, it's a finite sample. It improves the sample variance and can reduce the variance. We did some simple calculation to show that. And so this is how you. So that's the case. Relatively simple, right? This is just okay. And I didn't really show, and I think it's actually relatively easy to show that this estimator, it is unbiased. It's a consistent, yeah, I think it's consistent. At least this estimator will be consistent for the treatment effect tau. So that is kind of, so my first relatively simple question say that, well, if I have missingness in X and I still want to do covariate adjustment, but use weighting, how should I do? So that solves this question. But then the next question becomes, well, what if you have missingness in Y? Okay, so of course, what I really want to do is to solve the missingness both in X and Y, but I think it's important to first do the problem one by one. So now we move to the second problem. What if you have missingness only in Y? Okay, so things become much more complex here, well, more trickier here. So when you have missing Y, it's essentially to specify missing data mechanism of Y. This is very different from X. Okay, we know that missing completed at random usually doesn't make too much sense. That's actually precisely what complete unit study implicitly assume. But this is really questionable most of the time. So missing at random error is more plausible. So again, here I'm talking of missingness in Y, so I need another indicator. Missing data indicator I call RY. This one for outcome missingness indicator. Okay, so normally we assume it's missing at random. Basically, say that essentially the missingness of this doesn't depend on the Y itself, okay, only depends on the observed covariates and the treatment. So the central strategy of this, of course, is just to use the IPW of the, so if you have missing Y, what should you do? And again, this very famous paper by Seaman, I know Sean is not today's audience, but Seaman and White, this famous paper basically show that, well, you can just calculate the probability of missingness, and then for each being observed, for each observed unit, and then you just use IPW, reweight it, your analysis, and then you can get the unbiased estimator for the treatment effect that is in the target population. Okay, so that is all pretty well known. And then again, so what in this approach, what's the important thing, the key thing is you need to estimate it. You need to estimate the probability of Y missing, Y being observed. I call PI, for example, from a logistic model. But you need to estimate this probability being outcome observed for each observed unit, for each unit. And then once you estimate this thing, there are two approaches for covariate adjustment. The first approach, obviously, remember we were talking about the ordinary square estimator, the Ling's result. If you still remember, this is a Ling's result. Again, here is a case with only missingness only in Y. Remember this is Ling's estimator, it's just the coefficient of this, right? So now if I have missingness of Y, I calculate the probability of missingness for each y, then what I can do is obviously, instead of use ordinary least square, I can just use weighted least square, right? Weighted by the PI. So that's the length estimated. So I call that, we call that the WLS and the X because it's taking into account of X. So you just reweight the full interaction outcome model with those for to these observed units, use the IPW. Again, IPW on the outcome, okay? Outcome missingness. Or you can just, instead, you can also just purely just use the hierarchy estimator. Again, I wrote it here, complicated. Essentially, it's just you can calculate the weighted, again, the weighted difference between the treatment group and the control group, and I think here the weight is. So the point is that you calculate the weighted. So remember previously you can just weighted average, the difference of the weighted average outcome. And now you need to estimate, I think there's some mistakes here I wrote, but the point is you can just weight, just reweight the use IPW. Again, one is use weighted least square, the other is just purely weighted, use hierarchy estimator, but that's the idea. So those two are the covariate adjustment, but as I said that I have some, like here, I didn't write it very clearly, but the point is that you can do weighted least square or you can do IPW. So another approach is you can also do unadjusted estimator. Like you don't need to do covariate adjustment, you can just unadjust it. If you do unadjusted, so what you're gonna do is remember that's difference in mean. Now you just need to calculate the weighted difference in mean, and that mathematically is equivalent to do this. You're basically fitting also least square is just y given 1 plus b. Again, there's no interaction, no x. This is just purely this, and then the coefficient, and then actually reweight this, use the IPW weights. And this is, again, mathematically is exactly the same as actually the weighted unadjusted estimator. So this is, we call this WLS. This is basically unadjusted estimator when you have missingness. Okay, so what can I say? Yeah, those things are all great. But can I say something about those different approaches? Do I know which one is better? That's a result actually current, as I said, some freshly baked result we're currently working on. I work with Joan Ding recently. Again, this so what we found is, well, first of all, everyone knows missing y is of very different nature of missing x. So what we find here is theoretically we find that in the case of missingness only in y, and assuming the probability of missingness of y is correctly specified, we normally make that assumption, okay? Well, that assuming that is correctly specified, what do we find? Two very interesting things. Well, first, is the IPW estimator is asymptotically more efficient than the unadjusted weighted least square estimator. So basically, doing IPW with all the covariates with all the covariates asymptotically more efficient. Okay, so that justify why you do the covariate adjustment, but using use weighting. But somewhat surprisingly, we find the second result. We find that the weighted least square version of the length estimator basically reweight that interaction outcome model is also asymptotically more efficient than this unadjusted estimator, but that holds only under very stringent conditions. Actually, that includes linear model. It has to be only, it holds only if you have linear model and the heterogeneous treatment effect, additive effect across all units. So in other words, that this is actually the weighted least square version of length estimator is not necessarily more efficient than the actual unadjusted unadjusted estimator. So this is really surprising to us. Remember, in the case without missing data, we actually proved that there's a asymptotic equivalence between weighting and OLS. So I was thinking when I first look at this, when I first did start to work on this, I was thinking that, well, if you have missing at Y, missing at random, and we actually correctly specify the missing data mechanism, then I would expect that this asymptotic equivalence between these two different approach will extend to the case of missing Y. And it turned out not. So the point is that actually, when you do the weighted regression, it needs much stronger assumption or data structure in order to have the asymptotic efficiency gain. So this actually points to us that it seems that if you are missing Y, actually just to use the weighting estimator is sounds like a better idea than use the weighted least square. The weighted WS version of the Lynx estimator. And so that finding actually get us into the next step. Remember what I started with was, the question, how to do covariate adjustment when you have missingness both in X and Y. In order to solve that problem, I go this detour, first talk about the case of missing X, and then I investigate the case of missing Y. And from missing Y, this actually indicate to me that it's important to actually theoretically suggest that it's using weighting is a much better idea than use weighted least square. Okay, so then on to the third part of this question, this puzzle is how do I deal with the the covariate adjustments missingness both in X and Y. So well, again, in this case, now we're in the case of you have missingness both in X and Y. Okay, so in this case, we need to modify we still need to specify the missing data mechanism. So it's still MRI, but the thing is because now I have both missingness in X and Y, because I have missingness also in X, things start to be a little more complex. So I actually can have two different versions of MAR. I don't think I have much time to go into detail of that, but the point is just one is weaker than the other. Depends on whether you allow the missingness of Y to depend only on the fully observed covariates, or you actually allow it to also depend on observed values of a partially observed covariate. So there's some subtle differences, but the point is that this is just conditioning set different, but the point is that they are both MAR, and then one is weaker than the other. So you can essentially estimate the missing data, the probability of in Y actually accordingly to the assumptions you make here. So that is all relatively simple. Again, the point is that you can still use, for example, the regression just to calculate the missing data, the probability of missing data, and then you can use IPW. Okay, so well, now we have covariate adjustment. So we have both missing X, both in X and Y. Then, so how should we proceed? So again, as the theoretical result in the case with missing X, we know that a weighting approach to deal with the missing Y is probably better. And also, as earlier said, that if you're using the overlap weights, you also get the exact mean balance. If you have overlap, so the idea, and also conceptually, is more coherent. Just if you already go weighting, why don't we just weighting all the way? Right, so here we have the full weighting. So we propose a full weighting scheme. So what we do is we basically combine overlap weights for covariate adjustment and IPW to deal with the missingness in Y. So this is our new estimator. The estimator is a Hayek estimator for the treatment effect. Okay, so it's basically weighted average. Now the key thing is what is the weight? What is the weight? So the weight we're doing here is basically the product of the overlap weights for the covariate adjustment and IPW for the outcome missingness. Essentially, it's just the overlap weight times the 1 over p. Okay, so again, this is not too difficult to show that this estimator is consistent for tau, and if the outcome model is correctly specified. Again, this is kind of an important assumption. This is correctly specified. Actually, the nice thing is in the missing data so I need to do some more theory work here to also think of the robustness. But the interesting thing is the simulation we did, finite sample, we find that this is not too important. Well, like this is relatively easy to be satisfied. So again, so what we're doing here, we're after all this long detour, I proposed a full weighting scheme to do covariate adjustment when you have missingness, both in covariates and in outcome. What do is we first impute all the covariates, all the missing covariates. So this is approach. So this is algorithm. Basically, we impute all the missing covariate values by zeros. Oh, by zero. Sorry, it's just by zeros. This is a mistake. Just by zero. You can also use the means of this. Again, just use zeros is enough. And then what we do is then we estimate also the outcome missingness probability for each covariate, and using one of the depends on the missing data, the MRR assumption you make the covariates. Using one of those using the imputed data and use logistic model. And then also you need to estimate the working treatment propensity score for each unit using earlier the logistic model I mentioned earlier. Sorry, it's one of this model. Oh, it's this model. Yeah. Anyway, the key point is you need to put the missing data indicator. That's the main point. Okay. So the key point is both of those models need to include the missing data indicators, and then you just estimate the covariate adjustment treatment effect by the inverse weighted Hayek estimator, based on the units with observed outcome. It is separate here, specified here. Okay. So then we did some simulations. Again, the simulations and it looks pretty complicated. So I don't have time to talk about application, but I just go through the simulations. So simulation, we simulated a case that have 3 baseline covariates. One is highly predictive of the outcome and is partially observed. And then the outcome model is just linear, make life easy. We also compared 3 different missing data mechanism of X. We know that actually theoretically this doesn't matter too much. And then we also have, but Y, we know that matters, and we assume a MRR for Y. Okay, and so this is kind of the result. We show that, so again, we know that covariate adjustment works pretty well, like it's kind of useful when you have small samples. And so we create a case that you have 100 units and 30% missing data or 10% missing data, missing X. And also, what's the proportion of missing Y? I think it's around 10% or something. I forgot. But the point is that 30% is just 30% again. So what we should look here is RE is so-called relative efficiency. Basically, how the larger number, that means you have more efficiency gain. So relatively efficient, I think that's the case. So let's look at this. The higher this IPF4X, I think there's something going on here. I need to figure this out. But anyway, just look at the other look at the key point. So what is MI? MI is not multiple imputation, it's a missing indicator. Okay, so so this is approach essentially where we kind of advocate, right? We use IPW to deal with the and zero imputation. Well, you can also do mean imputation with indicator. But the whole point is that you can see that here is, this is whether you without. The key point is that with missing indicator and without missing indicator, you can see that there's the main efficiency gain happened here. Okay, and then you can see that doing the zero imputation, comparing zero imputation to the correct model imputation, actually the difference is relatively small. Okay, so that's the point. It's like whether you actually don't. When you have missing X, you don't need to get the X imputed correctly. Essentially, a zero imputation of covariates, that's enough. Okay, of course, here I didn't compare, and you can see the result is very consistent across different missing data mechanism across X. Of course, we didn't do, I think forgot whether we also did some simulation. Of course, this is about missingness in X, but if you have missingness in Y, then if you misspecify Y, then you're biased. That's kind of, we know that. But here, the key point is that you can see that the main efficiency gain happen actually when you include the missing data mechanism, missing indicators. And another thing is, as the theory predicted, it doesn't matter how you impute the missing covariates, as long put zeros is fine as long as you include the missing indicator. Okay, so you can see that here, like the wrong imputation, it doesn't, as long as you put the missing indicator here, there's no difference essentially. Okay. And so I have some application. I don't have time to talk about that. Well, the sad truth is, in practice, we almost all know that well, I don't know if it's a sad truth or whatever, but this is a case that this application, sample size is relatively big. Like I have 450 units, and I have something like 13% missingness in Y. And so, but in this case, the missing data is not a big deal. So it turned out that all methods are pretty similar. So there's some efficiency gain, but the result, well, you can still see that by doing covariate adjustment, you will gain around 7% efficiency gain. But then the methods actually, how do you do the covariate adjustment doesn't matter. It matters that you do it, okay? And so it's just a quick summary. I know that I'm kind of, I have should talk like 45 minutes, but I'm over time. But just quick summary. So what I did is I provide an overview of covariate adjustment in randomized experiment with missing data. And also, and this is particularly in the light of some recent theoretical advancement. And at the end of the day, we provide a full weighting estimator for covariate adjustment with missing outcomes and covariate. And also we find that, you know, as long as you do it properly, well, properly in the sense that include the missing indicator, the interaction between the X and the covariates and the treatment and the missing indicator properly, then weighting estimator, the estimator we propose achieves asymptotic efficiency gain over unadjusted analysis in both theory and simulations. And so, and interestingly, we actually find some new theoretical result. Covariate adjustment is missing X, missing Y, particularly this relatively surprising, like the asymptotic inequivalence, inequivalence between the ordinary square and the weighting is very interesting. And then one's future work is, well, this, you know, well, sometimes we do cluster randomized trial, and there usually the sample size is much smaller. And then how do you do covariate adjustment with missing data there? That become even, you know, more interesting question. And another thing is, again, people still don't use covariate adjustment that often. So it's, and despite all this theoretical advancement, so it's important to provide a very easy to use software, and people can just put their RCT data and then hit one button and then get a result. So we don't have that yet, so that is important to provide. So that is again some acknowledgements. It's really this. So the work, the missing X and Y work is with Jerry Chen, Yue Song, and Ray Wang at Harvard, and the theoretical result of missing Y is with Anqi Zhao, who's joining Duke soon, and Peng Ding of UC Berkeley. And thank you. And those are the key references. Yeah, thanks.
Thank you so much, Lan, for this great talk. I think it's very interesting. Also address very practical problems in analyzing data from trials. So if anyone has questions, you can speak. I think unmute yourself and speak, or you can put your question in the chat. So Ben, I have a question. I think it's quite interesting to see the worst performance of weighted least square compared to the.
Oh, you mean here?
No, in the theoretical results,
Yeah, this one, huh?
Yeah, the weighted least square actually perform. I think it is less efficient, or compared to the.
No. So this is, yeah. So result 2, right?
Yeah.
what we find that most of this is great surprising to us. We saw that for sure this weight least square should be more efficient, right? But it turned out that it's only more efficient only if I say very stringent conditions. What is a very stringent, including actually that only when the outcome of the true outcome of model is linear and it's homogeneous treatment effect. And this is hugely surprising because actually I didn't write it here. What happened is the WS of the length estimator, that thing we find is actually double robust. It's double robust in the sense that if both outcome model, it's double robust. It's local efficiency. But it's again theoretically improved, it's local efficient. But the funny thing is what happened here is once you have missingness in Y, then the coefficient, so the local efficiency, the kind of the interpretation of local efficiency changes. It's no longer like when you don't have missing Y, then the local efficiency basically means that, it's, so local efficiency, this local is problematic. So that's why I say that Link's result is actually stronger than Seada's result, because Seada's got this local efficiency, but Link's result is actually not local efficiency, just pure efficient, like more efficiency. So here, I mean, the theory is basically like we find that data need much stronger for this efficiency to hold, efficient gate to hold. The data need to have much stronger structure in the covariance structure. And again, we are still trying to figure out like an intuitive interpretation of this law. The math is for sure right. We checked. We first were so surprised that we checked again and again and find that the math is correct. And it's just again, it seems to be that what is really the interpretation of the local efficiency, and what we find is that yes, actually very often theoretically just doing the unadjusted weighted least square, not the link estimator, basically this guy, is actually more efficient, in most cases more efficient even than the WS version of that. IPW doesn't have that problem. As I said, that this is pretty striking because we saw that this asymptotic equivalence between weighting and OS will just trivially extend to this case with missing Y, but the result is not.
I think the weighted least square, you do use the original IPW weights. You don't you scale it like you do for the higher estimator, right? I think that might play a.
No, again, well, maybe I don't know. I because again we just work on this. I like literally now, so I
okay, it's work in progress.
Yeah, so I don't think it's the Hayek actually not using Hayek was the problem. I go back to check the math, and she did most of the math here. But that's a good place that I can check what's going on. That might be, but I don't think that's the main thing. We think it's more of the covariance structure or somehow.
It's just remind me of, I mean, because for the missing outcome data, you can also apply the balancing weights. It's just you have a different
no, you cannot. Actually, you cannot. so no,
I'm not saying the overlap weighting, but there are other like stable weights.
I see what you're following.
So it should have theoretically better performance than just fitting a logistic model.
But you can see that I actually don't think. Okay, now I see. I don't think that's really the Hayek, how you normalize is really a problem, because most of like extreme weights is not a problem here. Most of the time it's like you don't really have extreme weights, right? And also we already showed here that IPW actually is asymptotically more efficient.
But for the missing outcome data, you could have extreme weights. I mean, this is not. I know.
Oh yeah, that's true. That's true.
It's not for the balancing between treatment groups. I mean, we have a different balancing weights now. So you could apply the, I mean, most recent methods for like balancing weights for missing data. Sorry, I have taken up too much time. I don't know if anyone.
No. I think that's a very good argument. But if you look at result 1, we actually show IPW, just a raw IPW, without even this balancing weights as kind of better improve the weights. This is asymptotically more efficient. So
I think the IPW estimator you have is actually the Hayek estimator is having like I think it has a constraint. constraint on the weight, so it's bounded and
I
has a mean one. So it's unlike the original IPW weight, you have no whatsoever the constraints. So
that's a very good point.
So I think that's the difference. So if you apply the higher weight for the weighted least square, it may help, but I don't know. I mean, I don't know the theory, so it's just my experience.
The theory, I think you're right. Actually, when we did this theory, this part, we indeed didn't use Hayek. And so that's a good point. I'll go back to check the math and to think about it, because that's normally but yeah, that's a very good point. But again, this is very fresh, like we're just working on it, because originally we didn't think that this would be a problem. What we did is we were working on CRT. We just say, okay, let's first do the RCT, then there's a stepping stone for the theory. And then we find this thing rather surprising.
Yeah. I think it makes more sense if you combine the missing outcome, how you deal with that, and also the missing covariates.
Yeah,
I mean together, because those are very practical problems in reality. So yeah, does anyone have any other questions?
Question and
in the chat?
Oh yeah, some other slides. Yeah, I sent the slides already.
We can share the slides. I think we should have everyone's email if you register for the seminar. So we will send it afterwards. Fan, is it okay to share it with everyone who attended? Yeah.
Okay. Fine.
Yeah. Okay. So I'm actually also very interested in your work on overlap weighting. So question I have is for overlap weights, I think it's implicitly redefine the study population.
But it's not a problem here. So yes, in observational, you're absolutely right. In that's what I said. In observational study, so the overlap weight is changing the estimate, right? Change the estimate to the target population, to the population with the most overlap. That's in observational study, because the observational study, the propensity score is indeed, you estimate the propensity score to treat is the real treatment. But remember, as I mentioned, that in RCT, the true propensity score is actually constant. You don't need like the true propensity. So actually, like here, this is purely just the overlap weights or IPW is just purely a mechanical, like a numerical approach to.
So basically, it's a constant. I mean, if you have trials,
in trial doesn't change. It's actually we're still looking at the sample average treatment effect.
Okay. Yeah, it's just a different constant as you apply.
Exactly. Like this was just purely a numeric summary of the covariates that you're using this to balance the covariates, but it's not changing the estimate. But in observational study, it does.
Yeah. Okay. Thank you, everyone, for attending our BSU seminar today, and it's great to have Fan today, and thank you so much for attending. Thank you, Fan, again.
Thanks so much.
The great talk.
Yeah. Okay. Bye-bye.
Bye.